Welcome back to G Fun Facts Online. Today we are diving deep into one of the most fascinating detective stories in modern medicine. It is a story that requires us to change how we think about cancer entirely. Usually, when we talk about cancer, we talk about mutations. We imagine the DNA as a long instruction manual, and we picture cancer as a typo in the text. A letter gets swapped, a sentence gets deleted, and suddenly the cell goes rogue. That has been the dogma of oncology for decades. But today, we are going to look at a revolution in biology that suggests the problem isn't always the text itself. Sometimes, the problem is the bookbinding. We are going to explore the intricate machinery that decides which chapters of your DNA are read and which are glued shut. This is the world of epigenetics, and at the center of our story is a molecular mechanism recently dubbed the Menin Switch. This mechanism is a master lock found in some of the most aggressive forms of leukemia, specifically acute myeloid leukemia, or AML, and acute lymphoblastic leukemia, or ALL. For 30 years, this lock was considered unbreakable. It was an interaction between proteins that scientists called undruggable. They thought it was physically impossible to design a medicine to stop it. But today, that has changed. We have mapped the lock, and we have forged the key. So buckle up, because to understand this breakthrough, we first need to shrink ourselves down and enter the construction site of the cell nucleus. Let's start with the landscape. If you took the DNA from a single one of your cells and stretched it out, it would be 2 meters long. That is 6 feet of code fitting into a microscopic nucleus. To make this fit, nature uses a brilliant packing strategy. The DNA is wound around spools of protein called histones. This creates a material known as chromatin. Now this winding isn't just for storage. It is dynamic. It is breathing. When chromatin is wound tightly, the genes inside are hidden away. They are silent. When it is loosely packed, the genes are exposed and can be read by the cell's machinery. This is how a heart cell knows to be a heart cell and a brain cell knows to be a brain cell. They have the same book, but they are reading different chapters. The cell controls this reading process using epigenetic marks. These are chemical tags like sticky notes, attached to the histone tails that say, open this section or close that section. This brings us to the protagonist of our molecular drama, the MLL complex. In technical terms, it is the KMT2A complex. This massive assembly of proteins is a writer. Its job is to place a specific chemical mark, called trimethylation of lysine 4 on histone H3 onto the chromatin. Think of this mark as a green traffic light. It tells the cell, this gene is important. Keep it open for business. In normal blood development, this MLL complex is the master regulator of the Hox genes. Hox genes are the architects of the body. In blood cells, they control the balance between self-renewal, making more stem cells, and differentiation, becoming a mature white blood cell that fights infection. In a healthy system, once a stem cell decides to grow up, the MLL complex disengages. The Hox genes turn off, and the cell stops dividing and starts working. But in leukemia, this process is sabotaged. This brings us to part 2, the Menin scaffold. For the MLL complex to do its job, it cannot just float around aimlessly. It needs to be tethered to the DNA. This is where a protein called menin enters the stage. Menin acts as a scaffold, or a molecular hub. Interestingly, in other parts of the body, like the endocrine system, menin actually prevents tumors. But in the blood, it plays a paradoxical role. It acts as the critical anchor that holds the MLL complex to the chromatin. Visualize menin as a coupling hitch on a freight train. It connects the engine, which is the MLL complex, to the tracks, which is the DNA. Without menin, the MLL complex falls off, the green lights are erased, and the genes shut down. Now, let's look at the crime scene. In about 5 to 10% of adult AML and over 70% of infant leukemias, a chromosomal catastrophe occurs. The gene that creates the MLL protein breaks. It fuses with a partner gene, creating a chimeric monster called an MLL fusion protein. This fusion protein is a hyperactive tyrant. It keeps the part that binds to menin, but it swaps out its brakes for a superactivator. Because menin binds so tightly to this fusion protein, it locks it onto the genes responsible for stem cell growth, specifically HOXA9 and MEIS1. Normally, these genes are on only briefly. But this new, mutant complex forces them to stay permanently on. The cell forgets how to mature. It becomes trapped in a primitive, explosive state of growth. It becomes a blast cell. And here's a fascinating twist. This mechanism isn't limited to just those with the MLL fusion. In the most common type of AML, driven by mutations in a gene called NPM1, the cancer creates a chaotic environment that also relies on menin to keep these same leukemia genes turned on. This was a monumental discovery. It meant that different types of leukemia shared a single common dependency, the menin-MLL interaction. Scientists realized that this system operates like a switch. In the nucleus, there is a competition. There is the bad MLL menin complex that says grow, and there is a good complex called MLL 3/4 UTX that says differentiate. In leukemia, the bad complex is a bully. It physically pushes the good complex off the DNA. The Menin Switch hypothesis suggested a radical idea. We don't need to poison the leukemia cells with toxic chemotherapy. If we can just pop the menin protein off the MLL fusion, the bad complex will dissolve. This would allow the good complex to return, flip the switch, and force the leukemia cells to simply grow up and die naturally. But identifying the target is one thing, hitting it is another. This brings us to the challenge of the undruggable pocket. Menin is a globular protein with a large central cavity. For years, chemists looked at this cavity and despaired. It didn't look like a standard drug target. Usually, drugs act like a key fitting into a lock. But menin looked like a smooth, large wall. Trying to block the interaction between menin and MLL was compared to trying to stop a door from closing by throwing a marble at the hinge. It seemed impossible. However, high-resolution crystallography changed the game. Scientists mapped the menin structure down to the atom and identified a central pocket. It was a deep groove where the MLL protein inserts a tiny finger-like loop. This pocket was the Achilles heel. This led to the rise of menin inhibitors. Drugs like revumenib and ziftomenib were engineered to fit into this pocket with incredibly high affinity. The mechanism observed in the lab was nothing short of miraculous. The drug enters the nucleus and binds to menin. The MLL fusion protein, no longer able to hold on, falls off the chromatin. The open marks on the leukemia genes vanish. And then, under the microscope, something amazing happens. The leukemic blasts, which look like angry, featureless blobs, begin to change shape. They develop internal structures. Their nuclei change. They transform into mature white blood cells. They start to function. And then, because mature cells have a lifespan, they die. This is not cell killing in the traditional sense. It is cell reprogramming. When these drugs entered clinical trials, the results were electric. We saw patients who had failed 5, 6, or 7 prior therapies, people with essentially 0 options left, achieving complete remission. But the power of the Menin switch came with a unique risk, known as differentiation syndrome. Because the drugs work by forcing cells to mature, you can get a sudden burst of maturation. It causes a traffic jam of white blood cells in the body. As these cells differentiate, they release inflammatory signals, leading to fever and respiratory distress. It is a side effect that paradoxically proves the drug is working. Oncologists have now learned to manage this with steroids, turning a potentially lethal reaction into a manageable bump on the road to remission. Of course, biology always fights back. As with all targeted therapies, we are seeing resistance. The leukemia cells are under immense pressure, and they are evolving escape routes. One way they do this is by mutating the menin gene itself. They change the shape of that central pocket just enough so the drug can no longer fit, but the natural MLL protein still can. It is a molecular masterstroke by the cancer, essentially changing the lock so our key no longer works. Other cells find ways to rewire their epigenetics entirely, bypassing the need for menin. This means the discovery of the Menin switch is not the end of the story. It is just the opening chapter. The future of this therapy lies in combinations. Scientists are looking at pairing menin inhibitors with FLT3 inhibitors or BCL2 inhibitors like venetoclax. The idea is to hit the cancer from multiple angles simultaneously, programming it to die while also blocking its survival pathways. In conclusion, the Menin switch represents a paradigm shift. We have moved from bombing the city with chemotherapy to fixing the traffic lights with epigenetic therapy. By understanding the deep molecular architecture of how leukemia genes are locked open, we have found a way to pick the lock. While challenges like resistance remain, the clinical success of menin inhibitors proves a fundamental concept. Epigenetic dependencies in cancer are real, they are powerful, and they are actionable. For patients, this offers something that has been in short supply for decades. Not just a treatment, but a precise mechanistic hope. The lock is broken, the genes are silencing, and for the first time, the cell's own machinery is being turned against the malignancy it once sustained. Thank you for listening to G Fun Facts Online.